Okay, hello everyone in a new video. So we have reached part 9 of chapter 5, which is the chapter of kinematics for grade 11 students. So in this part we are going to solve some exercises. So we have reached exercise number 21. They are telling me in a two-dimensional motion, the acceleration vector of a moving particle is given by A is equal to 3I. The initial vectors are given by R0 is equal to 3I and V0 is equal to 6G. So before we start solving this exercise, let me split these vectors into its components. Then A is equal to 3I, means that the x component is equal to 3 meters per second square. As for its y component is equal to 0. The initial position vector is given by 3I, which means that x0 is equal to 3 meters and y0 is equal to 0. As for the initial speed, which is equal to 6j, then the initial velocity along the x-axis is equal to 0, whereas the initial speed or velocity along the y-axis is equal to 6 meters per second. Now in number 1 they are telling me represent the initial vectors r0 and v0 in the xy plane, and by represent it means that we need to draw. So let's consider an xy plane. So these are the positive directions. This is the origin O, knowing that the x-axis is being described by the unit vector I. As for the y-axis is being described by the unit vector j. Along the x-axis it carries the quantity, which is the position along the x having the unit meters, and as for the y-axis it carries the unit the quantity y, position along the y having the unit meters. So notice that these x and y are different than that of the mathematics. These are physical quantities corresponding for the positions and not just any labels. Okay, now let's start by representing the initial vector r0. So notice that in order to represent any vector in a coordinate system, we need to take into consideration its point of application and the head of the vector. Okay, always the point of application of any position vector is the origin O. Now as for the head of the vector is determined by this point, which is 3, 0. So 3, 0 and this plane corresponds to this point, 0 on the x-axis, sorry, 3 on the x-axis, so 1, 2, 3, and 0 along the y-axis. So this is the head of the vector, and it's being oriented from O to this point. Okay, then this represents the initial vector r0, and in this case if we name this particle to be the point M, then the point M will be located here, because what does the position vector represent? It represents the position of the vector. So always the particle is being located on the head of this vector. So we are done with r0. Now as for v0, the point of application of the velocity vector is the center of gravity of M, so this is the point of application of v0. So now we need to represent v0 starting from this point. It may be like this, like this, like this. Okay, so this depends on the coordinates of this point. So notice that v0 is equal to 6j, which means it is 0, 6. Now we need to locate the point 0, 6, but in this case we don't consider the origin as the starting point, whereas we consider the point of application of the vector to be the origin. So counting 0 from this point, so we are still here. Now counting 6 upward representing y, so we have 1, 2, 3, 4, 5, 6. So this is the head of the vector, 1, 2, 3, 4, 5, 6. Now if we join these 2 points, then this is the initial vector v0. Let me say this is the point 6, 0. Okay, without, because it will be confusing. Okay, so this is it for number 1. As for number 2, They are telling me specify the type of motion along the x-axis and the y-axis. So we are decomposing the motion in 2 dimension into rectilinear motion along the x and along the y. So it's convenient to write on the scratch the equations of motions regarding one dimension, and they are given by, for the URM, x is equal to vt plus x0, v is equal to a constant, as for the acceleration is equal to 0. In the case of UVRM, we have that x is equal to half at squared plus v0t plus x0, in which v is equal to at plus v0 and the acceleration is equal to a constant. Now let's start by justifying the type of motion along the x-axis. Now, position vectors are useless in determining the type of motion, so we always need to refer to a general equation which is given by this. So a of x is equal to 3 meters per second square, which means it's equal to a constant different than 0 than we are in the case of UVRM along the x-axis. Since a of x is equal to 3 meters per second square verifies the general form. A of x is equal to constant. Then the type of motion is UVRM along the x-axis. As for the y-axis, now the acceleration along the y-axis is given by 0. Whenever the acceleration is given by 0 along an axis, then it is URM. Since a of y is equal to 0 verifies the general form. Then the type of motion is URM along the y-axis. Now in number 3 they are telling me determine the velocity, and the velocity is a vector quantity consisting of 2 components in 2 dimensions, which is given by v is equal to vxi plus vyj. In order to determine v, the velocity vector, we need to determine its x and y component. Let's start by the x-axis, and let me say here that we have justified previously that the type of motion is UVRM. Now, since the type of motion is UVRM, then in this case the following equations hold. X is equal to half at squared plus v0t plus x0. V is equal to at plus v0, and a is equal to a constant. And the mistake that I have done here is that all of these quantities must carry a label distinguishing between the x and y. So this is x, this is x, okay, except for time. Now in this case the general form is given by ax is equal to 3 meters per second square. Notice that we are interested in determining vx, which means we need to specify ax and v0x. Already ax is being specified, whereas for v0x, from the given, okay, v0x or vx0 is the same, so this is 0. In this case, vx is equal to 3t plus 0, which is equal to 3t. Then the speed along the x-axis is given by 3t, or the velocity. Now as for the y-axis, the type of motion is being specified, which is given by URM. And let me say, since the type of motion is URM, in this case the following equations hold, which is given by y is equal to vt plus y0. v is equal to a constant and a is equal to 0, and the mistake that I have done here is that all of these must carry components. They are given by y, y, y. In this case, the general equation is given by ay is equal to 0. Now we are interested in determining vy, which is a constant, so it's sufficient to determine vy at a given instant. And in particular, we have vy at the initial instant, which is given by 6. Because vy is constant at all instants, then in this case vy is equal to vy0 is equal to 6 meters per second. So vy is equal to 6 meters per second. After we have determined the x and the y component of the velocity, then the velocity vector is given by 3ti plus 6g. Now in the same part they are telling me to deduce the instantaneous speed, and by deduce it means that we need to use the previous part. The instantaneous speed is deduced from the instantaneous velocity. Notice that this is the instantaneous velocity because it explicitly depends on time. Then knowing that speed is the magnitude of v, dropping down the vector, then v is given by square root of the sum of its component raised to the power 2, which is given by 3t to the power 2 plus 6 to the power 2. So the speed in this case, the instantaneous speed, is given by 3t to the power 2 plus 6 to the power 2. So notice that this we name it as the instantaneous speed because it explicitly depends on time. Now here, as a good habit, we don't expand what is inside the radical, and we keep it in the factorized form, okay? So this expression consists of two groups. This is the first group and this is the second group. So usually we don't factorize and reduce, we don't expand and reduce these expressions, okay? Now in part 4 they are telling me determine the position vector, which is by definition given by r is equal to xi plus yj. Now x that we have specified previously is given by half axt square plus v0xt plus y plus x0. The value of ax is given by 3. The value of v0x is given by 0. And the initial position along the x-axis is given by 3. Then this is equal to 3 over 2 t to the power 2 plus 3. As for y, which is given by vyt plus y0, the value of vy is given by 6t. The value of y0 is given by 0. So this is equal to 60. Then the position vector in this case r is given by 3 over 2 t square plus 3 multiplied by the unit vector I plus 6t multiplied by the unit vector j. And notice this is a vector definition, then vectors must exist on the left and on the right. Now in number 5 they are telling me determine the tangential unit vector. The tangential unit vector is by definition the ratio of the velocity over the speed. The velocity is given by 3ti plus 6j divided by its speed, which is given by this. So notice this is a vector definition. Vectors must exist on the left and on the right. This expression consists of two fractions having the same common denominator, which is this. Then let's split these fractions in order to identify the x and the y component. So in this case, this represents the unit vector u tangential. So this is its x component utx, and this is its y component uty. Now they are telling me to verify that its magnitude is equal to 1. Then the magnitude of any vector can be done by dropping down the vector and taking the square root of the sum of its component raised to the power 2. Now this is the x component. And this is the y component. Now this power 2 is for both the numerator and the denominator. So it's given by 3t to the power 2 divided by the denominator, which is given by 3t squared plus 6 to the power 2 plus. Now as for this power 2 is for the numerator and the denominator. Then the power 2 cancels out the radical and we have 3t squared plus 6 squared. So notice that these fractions have the same denominator, which is this, then it's equal to. Now we can add up the numerators. So independent of the value of time, the numerator is equal to the denominator, which is equal to square root of 1, which is equal to 1. Then the magnitude of the tangential unit vector is equal to 1. Notice that all quantities in physics must have unit, but it happens sometimes that quantities are dimensionless, and this case is one of them. Remember that all unit vectors are dimensionless. Unit vectors are essential in describing line of action and direction, okay? Whereas the magnitude itself, it contains the unit, okay? Now part 5, let me do it here. And let me write the value of the position vector, which is given by 3 over 2t squared. So the position vector r in this case is given by 3 over 2 t squared plus 3i plus 6tg. Now in part 6, they are telling me to calculate the average velocity between the instants t1 and t2. So always as a first step in physics, we need to write the definition of the quantity that we are interested in calculating. The average velocity is the ratio of the displacement over the duration, which is given the final instant minus the initial over the final minus the instant, and the final and the instant are determined by referring to times. So notice that because 4 is greater than 1, that this is the final, this is the initial. So we are computing the difference between the positions vector between the instants t1 and t2. Now in order to determine these fractions, we need to compute r at the instants 1 and 2, and in this case this is a scalar quantity which is given by 3, 4 minus 1. So r1 corresponding for the position vector computed at the instant t1, which is equal to 1 second. Now replacing t by 1, we have 3 over 2 multiplied by 1 plus 3. Plugging this fraction in the calculator, then it's given by 9 over 2 multiplied by the unit vector I. As for this, it's given by 6j. Now as for the position vector computed at the instant 2, corresponding to 4 seconds. This is equal to 3 over 2 multiplied by 4 because to the power 2 plus 3. Plugging this on the calculator, then it's given by 27i, and 6 multiplied by 4, it's 24j. Now we are ready to calculate the difference delta r, which is equal to r2 minus r1. The expression of r2 is given by this, and the expression of r1 is given by this. Now taking I as a common factor, here we have 27, so minus by 9 over 2 plus j, which is 24, minus 6. Then in this case delta r is equal to 27 minus 9 over 2 is given by 45 over 2j, I. As for 24 minus 6 is given by 18j. Okay, so this is the value of delta r. Now we are ready to calculate V average. Then in this case V average is equal to 45 over 2i plus 18j divided by t2 minus t1, which is equal to 3 because 4 minus 1. So now this is a vector definition. Vectors must exist on the left and on the right. So 45 over 2 divided by 3 multiplied by the unit vector I plus 18 over 3 multiplied by the unit vector j. Then 45 divided by 2 divided by 3 is equal to 15 over 2 because this is an irreducible fraction, multiplied by the unit vector I, and 18 divided by 3 is equal to 6j. Then the average velocity between the two instances that are being specified is given by 15 over 2i plus 6j. So this is a vector quantity. We can determine the average speed between these two instances by considering the magnitude of this vector. Sorry. Okay. And here let me write that the velocity vector is given by 3ti plus 6j. And now in part 7 they are asking me to calculate the average acceleration, which is by definition given by the variation in the velocity divided by the duration, knowing that this is the final instant and this is the initial instant, so it's given by v2 minus v1 divided by t2 minus t1. v2 is the velocity computed at the instant t2 is equal to 4 seconds, so it's given by 3 multiplied by 4 is equal to 12i, and this is independent of time, plus 6j. As for v1, which corresponds for v computed at the instant t1 is equal to 1 second, is given by 3 multiplied by 1, which is equal to 3i, plus 6j. So now delta v, which is equal to v2 minus v1, 12i plus 6j minus 3i plus 6j. As you can notice that the y component cancel each other, and this is given by 12 minus 3 multiplied by I as a common factor, which is given by 9I. So now the average acceleration is given by 9I divided by delta t, which is equal to 3. So this is equal to 3I. And here, as expected, since the acceleration is constant, then the average acceleration will be equal to the instantaneous acceleration, which is equal to 3I. So that's it for exercise number 21. Let's move to exercise number 22. They are telling me in a two-dimensional motion the acceleration vector of a moving basketball is given by A is equal to minus 10J. Which means that the acceleration along the x-axis is equal to 0. And the acceleration along the y-axis is given by 10 meters per second square. At t equals 0, the basketball has the following conditions. So we have that the initial position vector is given by 2j, which means that x0 is equal to 0 and y0 is equal to 2 meters. And as for v0, it's given by 3i plus 4j, which means that the x component of the speed initial is given by 3 meters per second, and the y component for the speed is given at the initial state is given by 4 meters per second. Now in number 1 they are telling me represent the initial vectors r0 and v0 in the xy plane, and this is important in order to describe the scene of throwing the basketball. So if this is the x-axis, and this is the y-axis, these are oriented axes x, y, this is the origin O, this is the unit vector I, this is the unit vector j. So recall that unit vectors are essential in encoding the line of action and the direction, okay? These x and y are different than those in mathematics. This is a physical quantity having the unit m, representing the position as well as for this. Now let's start by r0. In order to represent a vector, we need to indicate its point of application and line of action. Always the point of application of the position vector is the origin. Indicating point of application and the head of the vector. The head of the vector is determined by this point, which is given 0, 2. Now locating this point in this system, so 0 we are here and we go to up, so this is the head of the vector. So this vector r0 having point of application origin. This is the head, represents r0. So what do we benefit from r0? If this basketball is being labeled, for example, by B, then the basketball at the instant t0 is being located at this point. So here we have the basketball. So let me draw a basket here, basketball. So the basket is located at this location at the instant 0, okay? t0 equal to 0 at the initial instant, t equal to 0. Now we need to represent the vector v0. So in order to represent the vector v0, first we need to identify its point of application, and always the point of application is center of gravity of the particle or the object, which is the basketball. So we will draw the vector v0 starting from here, taking this as an origin. Now in order to represent this vector, we need to identify its head, which is given by 3, 4. Now we need to locate 3, 4 in this system, but considering that this point is the origin, so we move 1, 2, 3 and we go for up 1, 2, 3, 4. So this point represents the head of the vector v0. So what does this mean? This means that the basket is placed here. So suppose that somebody is holding the basket like this, and he is throwing the basketball to reach the basket that is located here. So the trajectory in this case will be something like this, that it reaches the ball and hit the ground at this point, say for example. Okay, now in number 2, they are telling me determine the velocity. We deduce the instantaneous speed. In order to determine the velocity, we need to discuss the type of motion along the x-axis and the y-axis. So let's start by the x-axis. So the velocity is given by vxi plus vyj. So as for the x-axis, so since, okay, let me here write between on the scratch the equations of motions for urm and for uvrm. So x is equal to vt plus x0, v is equal to a constant, and a is equal to 0. Whereas for uvrm, we have that x is equal to half at square plus v0t plus x0, v is equal to at plus v0, the acceleration is equal to a constant. Now we need to refer to the given. So in the initial vectors, they don't give us any information about the type of motion. We need in this case to refer to the acceleration. In this case, the acceleration along the x-axis is equal to 0, which verifies that the general form of URM then the type of motion is URM along the x-axis, and by this we can directly use these equations that are given by x is equal to vxt plus x0, vx is equal to a constant, ax is equal to a 0. Now in this case we are interested in determining vx. In order to determine vx is equal to constant, so it's sufficient to determine vx at any instant, and in this case we have vx0 which is equal to 3. So vx is equal to vx0 which is equal to 3 meters per second, and this is because vx is simply constant, so we can specify vx at any instant, and in this case vx is equal to 3 meters per second. And this is reasonable because here only the acceleration occurs on the y-axis. And now as for the y-axis, let me say since the value of a of y in this case is given by minus tan, verifies the general form a of y is equal to a constant, then the type of motion is uvrm along the y-axis, and now we can directly use that y is equal to half at square plus v0t plus y0, and here we need to distinguish between different components, so this is yy, vy is equal to ayt plus v0y, and ay is equal to a constant. Knowing that we are interested in determining vy, which means we need to determine ay and v0y. In this case, ay is given by minus 10 meters per second square, and referring to the initials, we have that v0y is given by what? Is given by 4 meters per second. So if vy0 or v0y it's the same. So in this case, the expression of vy as function of time, because it explicitly depends on time, is given by minus 10t plus 4. Now we are ready to express the position vector, which is given by v is equal to 3i plus minus 10t plus 4j. Now in part 3 they are telling me determine the instant at which the velocity is parallel to the x-axis. So here in this case we need to determine time, knowing that the condition is given by the velocity is parallel to the x-axis. So the velocity vector that we have determined is given by so v in this case is given by 3i plus minus 10t plus 4j. So they are telling me determine at the instant t at which the velocity is parallel to the x-axis. So as the ball is moving like this, we can define at any moment. So suppose the ball reaches this point at the instant t, the velocity vector will be tangent to the trajectory. So this is v. Okay, we are interested in determining the instant at which the velocity is parallel to the x-axis. So when is the velocity parallel to the x-axis? When it has the following form. So this is a velocity vector is parallel to the x-axis, having vxi plus vyj, but because it's parallel to the x-axis, then the y component is 0. So whenever a vector is parallel to a given axis, the another component is 0. So in this case, since it's parallel to the x-axis, so simply the other component, which is y of the velocity, is equal to 0. And let me here say since it is parallel to the x-axis, then v of y is equal to 0. But v of y is equal to minus 10t plus 4, knowing that we are interested in determining time. What's the type of this equation? Linear equation and time. Then 0 is equal to minus 10t plus 4, which means t is equal to 4 divided by 10 seconds. And notice that this is a positive number, so this is accepted. So the time at which the velocity of the ball is parallel to the x-axis is given by 2 over 5, which is equal to 0.4 second. So this instant corresponds for the instant in which the velocity of the ball is parallel to the x-axis. Now in part 4 they are telling me determine the position vector, which is by definition given by r is equal to xi plus yj. The expression of x is given by vxt plus x0, knowing that vx is equal to 3, t, as for x0, if you refer to the initials, is given by 0, so this is 3t. As for y, which is given by half ayt square plus v0yt plus y0, the value of ay is given by minus 10. So notice that ay is given by minus 10, v0y is given by 4, whereas y0, if you refer to the initials, is given by, I think, 2. So y0 is given by 2. So in this case, the expression of y is given by minus 5t square plus 4t plus 2. So the position vector r is given by minus 5t square plus 4t plus 2. Okay. Now in part 5 they are telling me write the expression of the instantaneous speed of the basketball as function of time. And the instantaneous speed means that we need to refer the instantaneous velocity. This is the instantaneous velocity. Okay. So it has 4 properties. So this is the instantaneous velocity because it explicitly depends on time. Then the instantaneous speed is given by square root of vx square plus vy square, which is equal to the square root of 3 to the power 2 plus minus 10t plus 4 to the power 2. Okay, so this is the instantaneous speed. For sure it is expressed in second, and recall that we don't expand what is inside the radical, we keep it in the factorized form, although it exists of 2 groups. They are telling me in part 6, determine the tangential unit vector, then verify its magnitude is equal to 1. Then the tangential unit vector is by definition given by the ratio of the velocity over the speed, which is equal to 3i plus minus 10t plus 4j divided by the speed, which is given by the square root of 3 square plus minus 10t plus 4 to the power 2. So here we have, okay, this is a vector definition. Vectors must exist on the left and on the right. Now let's split this 2 fractions having the same common denominator into 2 fractions. Then it's given by 3 divided by square root of 3 to the power 2 plus minus 10 t plus 4 to the power 2 multiplied by the unit vector I plus minus 10t plus 4 multiplied by the unit vector j, normalized or divided by this fraction, which is given by 3 to the power 2 plus minus 10t plus 4 to the power 2. So this is the tangential unit vector at an instant t. Then they are telling me to verify that its magnitude is equal to 1. So because it's a tangential unit vector, so from its name unit vector, we expect that its magnitude is given by 1. So this is a vector, this is its x component utx, and this is its y component uty. Then its magnitude ut is given by the square root of utx square plus uty square. Then its x component is given by this, raised to the power 2, plus its y component raised to the power 2. So now this power 2 is for the numerator and the denominator, and it's given by this 9, okay, or 3 to the power 2 divided by 3 to the power 2. So the power 2 cancels out of the radical, plus minus 10t plus 4 to the power 2 plus this raised to the power 2, and the power 2 for the denominator cancels out of the radical. It's given by 3 to the power 2 plus minus 10t plus 4 to the power 2, which is equal to, so notice that these 2 fractions have the same denominator, then 3 to the power 2 plus we can add the numerators, and independent of the time, the value of time, notice that the numerator is equal to the denominator, so the value of this fraction is equal to square root of 1, which is equal to 1. So this is equal to square root of 1, which is equal to 1. And recall that here no unit for unit vectors. Okay, so it's a dimensionless quantity. Now in part 7, the final part, they are telling me at what instant will the basketball reach the ground. So at what instant means that we are interested in determining time, and in order to determine time we need to transfer this statement into a mathematical condition called the constraint. So this is the scene of the throwing of the basketball, knowing that we are interested in determining time when the basketball hits the ground. So suppose that this is the ground, and we throw the ball like this, it will reaches the ground, okay? So we need to transform the statement reaches the ground into a mathematical statement called the constraint. and reaches the ground. So we don't know the position for x, but we know that y is equal to 0. And this is an equation. By setting y is equal to 0, we can solve for t. So let me say, since it reaches the ground, then in this case y is equal to 0. But what's the expression of y as function of time? So what is this? This is wrong here. Let me correct it. So the position vector here is given by 3ti. So as I have said previously, vectors must exist on the left and on the right. Plus minus 5t square plus 4t plus 2, okay, j. So this is the expression of y. We have minus 5t square plus 4t plus 2 is equal to 0. Okay, what is it? Minus 5t square plus 4t plus 2 is equal to 0. Now we need to solve for time. What's the type of this equation? We take the highest degree, so this is a quadratic equation. Then what are the solutions of these equations? Either two distinct roots, double root or no roots, and this depends on the sign of delta, but we can directly use the calculator. So plugging this on the calculator, we get that the first root is given by t1 is equal to 2 plus the square root of 14 divided by 5, and the decimal form is approximately equal to 1.15 seconds. As for t2, which is given by 2 minus radical 14, okay, here you can solve this explicitly by determining the discriminant delta. Then the roots are given by t1 minus b plus radical delta over 2a. Then t2 will be replacing plus by minus. So this is approximately given by minus 0.35 seconds, but we know that it will reaches the ground only at what instant? For the first instant. So, and time is always positive, so this is positive accepted and this is negative rejected. Then t1 represents the instant at which the basketball reaches the ground. Okay, and by this we have finished solving this exercise. So that's it for me in this video, guys. And the next part will also complete solving exercises on this chapter.